Hello everyone, I'm Deborah Caldarola and I'm here to introduce you our work improving generalization in federated learning by seeking flat minima. A few things you need to remember about federated learning. It's a distributed machine learning framework in which the client's data is privacy protected, and that is why we move training on the client side instead of moving the data to the server side. As for the server side, we simply aggregate the trained models, usually using FedAVG, which simply averages the updates. The focus of this work is on heterogeneous federated learning, meaning that the client's data is non-IID with respect to the global distribution, and the local datasets are imbalanced in their sizes. Why do we care? When we train models in heterogeneous scenarios, we'll see how the learning trend will be unstable and noisy, and we'll see a significant gap in performance with respect to models trained in homogeneous scenarios. The hypothesis at the basis of this work is that since local distributions are heavily skewed and the local model only sees a subset of the tasks, it will be likely for the model to overfit the client's data, and the resulting global model will not be able to generalize to the overall underlying distribution. So first, we analyze the behavior of the models in federated scenarios and find out that they converge to sharp minima, which are linked with poor generalization by recent literature. So to encourage convergence towards flat minima, we apply Sharpness-Aware Minimization on the client side and stochastic weight averaging on the server side. We test this approach on multiple vision tasks, such as large-scale classification and domain generalization. Lastly, we show how an approach usually used to improve generalization, which is the usage of strength data augmentations, fails in heterogeneous federated learning. Now, a few details on the method. Stochastic weight averaging and sample points found by SGD during its optimization path. The idea is that the average of the weights found by SGD will be closer to the center of the minimum instead of lying on the edge, and that will improve performances. We apply this method on the server side to ensemble global models across rounds. Sharpness-Aware Minimization instead seeks flat minima during training. The idea is that we don't want to find a single point having a low loss value, but we want to find a neighborhood of a given side in which all points have a low loss value, and we do that by minimizing both the sharpness and the loss value. We apply not only SAM but also its adaptive version, which is ASAM. This method is applied on the client side to encourage convergence of the local models towards flat minima, so that once we average them on the server side, we will have a more robust model. We show now results on CIFAR 100 in which each client only sees one class, and we invite you to check out our paper for results on additional tasks and datasets. So in this case, we see that when we train models with SAM or ASAM, the global model will actually converge to flat minima, which is what we wanted. As for the results, when we combine SAM and stochastic weight averaging, the global model is able to reach convergence even in the most heterogeneous scenario. One might wonder if these improvements are simply a reflection of the gain that we have in the centralized scenario, but our experiment shows that that is not the case. In fact, we can see how the improvement obtained in the heterogeneous federated scenario is much larger than what we get in the centralized one. In addition, as mentioned before, standard augmentations that work in the centralized environment fail to do so in the federated one, and that is because they encourage overfitting on the client's data. You can find here the main references of this presentation. And I thank you very much for your attention and invite you to come find us at the poster session in Tel Aviv. Otherwise, this is the contacts to find us, and thank you all again.